Hello everyone, welcome to the international webinar on solar photovoltaic system. This is the fifth webinar organized by the Department of Mechanical Engineering, Jyoti Engineering College. We are happy to have participants from more than 10 countries. And today we have with us Mr. Rajat Shashidharan, Senior Project Engineer, Power Green ME, Doha, Qatar, to handle this session. He is the right person since he is working in this field for more than 6 years, especially in design, building, testing, and commissioning of renewable energy installations, particularly in solar and wind power. He completed his bachelor's in mechanical engineering in 2011 and has a postgraduate diploma in energy management. Let me invite Mr. Rajat Shashidharan to handle this session.
Perfect. We are all set here. Please come in the chat window in case if my audio is not coming to you. I believe the audio is clear. Jidin, can you please confirm the audio is clear?
Yes, the audio is clear.
Perfect. Well, welcome to the field of solar photovoltaics. There are different kind of solar applications in the world. Here we are only discussing about the photovoltaic part. Yes, photovoltaic is something that produces electrical energy, and there is another method of producing electrical energy that's called concentrated solar farms. We are not covering that because it's more associated to the solar thermal energy, because there the light is getting reflected and here the light is getting absorbed. Yes, we have this handy fusion reactor in the sky. You don't have to do anything, it just works. Shows up every day and produces ridiculous amounts of power. This is said by Elon Musk. Some of you may have seen him and heard his speeches, and he's a brilliant guy. And there's a very good quote about the sun. And what is this ridiculous amount of power that he's talking about? That is 3.864 times 10 to the power of 26 watts. Yes, that's 3.8 septillion watts. That's crazy amount of energy. This is every second that is getting emitted out of a sun. Let me stop the camera feed just to get more clarity here. Sorry. Perfect. Anyway, so this 3.864 times 10 to the power of 26 watts is just produced at the sun's outer layer, and it is not coming to the earth. When it reaches earth, we start quantifying that in another terms. It's called watts per meter square, and we receive somewhere around 1,300 watts per meter square. In this presentation, we'll be covering through these topics, that is fundamentals. Please be informed in advance itself. This is not a theory-oriented class. This is more or less industrial-oriented class. I'll be helping you to familiarize with the industrial part or the construction part of a photovoltaic system. Then we'll go to various types of solar systems in action. We can see a little bit about the design criteria. Again, it is not a theory side, because getting into the theories of design criteria, it takes a lot of hours, several hours to familiarize with. Then we'll see how the project management works in our industry. Then we'll go to the testing and commissioning, and ultimately the scope for engineers. What kind of engineers and how and where do you fit inside the industry? Let's start with photovoltaics. We are ignoring the quantum mechanics part here. Maybe you can browse it up later. Then here is just an introduction, because academically either you may have already come across this topic or else you are about to come across this topic. So this is just to brush up. Photon is a packet of energy, as you all know, and it is just a byproduct of a nuclear reaction, right? So that photon it encompasses the electromagnetic radiation, out of which we can see a small portion, that's the visible light. And when this light hits a PN semiconductor, it gets biased and it produces an EMF, right? So there it builds a DC voltage. So from this DC voltage, we draw the current. That's the simple and the basic mechanism associated with the photovoltaics. You may have seen a solar panel at some point of your life, but this is for those who haven't got a chance to have a closer look. What are the equipment or how it is made, the solar panel? As you can see here in the screen towards the center, you will find a blue thing with a lot of squares. That's called the solar cells. And each cell is a panel itself because that's the producer, or that's the point where the energy is being generated. The electrical energy is being generated. And these cells are connected in series, and several of such series, or either parallel also, because it is purely depending on the manufacturer specification and how do we need the solar panel to be produced. But in general, the ideal solar panel that you find in a market, the cells are connected in series, and it is double encapsulated. Why double encapsulation? Because this is a metal inside and there is a semiconductor inside which tend to corrode and oxidize. So to protect it, they make this sandwich really airtight. And for an added protection, they put a tempered glass on top of it. There is about 5,400 Pascal is the strength of the glass. It's because, in different part of the world, it hails, and there is a snow load as well. So it's just for an impact resistance. Okay. It is given with the backsheet again, and everything is encapsulated in an aluminum frame. Why aluminum? Because of its corrosion resistivity. Now you can see this small box behind the panel. It's called junction box. This is where all the bus, in this photo you can see the bus of a solar photovoltaic panel, how it is soldered, and this bus is terminated behind this panel in the junction box. That's the place from where we can plug in our wire and how we are going to extract the energy out of it. And most importantly here, these junction box consist something called bypass diodes. And why do we need bypass diodes? It's because, at times when we combine these panels to make a solar photovoltaic plant, we may put these panels in series. So when you put these panels in series, the continuity is a big concern, because what if one of the panel is gone? Yeah, it's defective. In that case, these bypass diodes assures the continuity of the string. These are some of the photos. There are different kinds of applications. One of the beauty of solar photovoltaic is that it is very flexible. You can put it in parallel if you are, you can put it in flat in case if you are in an equatorial country. A tilted installation on a ground, it's possible. Similarly, a tilted on roof is possible. And the flower thing that you see, it's a state-of-the-art smart flower. This is a photovoltaic system, and it actually tracks the sun. That's a 2 kilowatt solar photovoltaic plant that you see in the flower. This is another beauty of the solar photovoltaic system, that you can actually use the waste space on top of a roof in order to harvest as much as energy as possible, and it's really green, and it really aids to the cutting the carbon emission. There are two types of tracking mechanism. What you see in the photo is not a tracking mechanism, it's just a static installation, so you can refer to the arrows. Yeah, depending on the need, you can have the access, because this tracking mechanism is actually done in very large photovoltaic plants where there are megawatts scales of installation is associated. So the single axis tracking is on one axis. Basically, you can see it can either go, it just tilts in one axis, right? And if you see the dual axis tracking mechanism, it has two axes. It can go up and down, and it can go sidewise. So more close you are to the equator, you may only need a single axis tracking, or you just need a flat installation or just a tilted installation. But as you go farther from the equator, you may need better access, better tracking mechanism in order to harvest energy. Of course, this comes at a heavier cost because there are so much mechanics involved. So often we check the financial viability of having a tracking mechanism, and we try to estimate how much energy we are getting out of the system. Before we proceed any further, there are some terminology that we need to understand, and that's the watt peak, because I've heard several people rate, they rate the panel with watts. No, that's not the right way in the industry. It is always watt peaks. So if you talk about a solar photovoltaic plant, then it is rated in kilowatt peak or megawatt peak. And let's understand what is this peak. As you know, there are several variables associated to a solar photovoltaic panel. Yeah, the sun is the angle of sun, the intensity of the light, the temperature of the module, everything is basically variables. Yeah. So when they standardize these tests, they test with 1000 watt per meter square. That is the intensity of the light or the irradiation, and they keep the module temperature at 25 degrees Celsius during this testing purpose, and keep the air mass at 1.5. That's also important because there is a spectrum and we have an air density and the incident angle. So they consider air mass to be 1.5 and do the testing at the panel. So when they do this testing, they will get the below mentioned results. So let's see. Let's start with the UOC. Its UOC can be VOC. VOC means open circuit voltage. So you see it's 37.84. I have highlighted one line here in the bottom. It's 37.84 volts, right? Then the short circuit is 8.85. So these are the two preliminary factors. So next thing is understanding what is the maximum power point. So when you have a closed circuit photovoltaic system under testing, then you will get something called the voltage at maximum power point. As we all know, in a short circuit system, the voltage drops as the current starts getting out of the circuit, right? So that's the voltage at maximum power point. It's, let's say, VMPP, and we have an IMPP. IMPP means it's the current at maximum power point. Here I've put a graph to understand how this works, because as soon as the panel starts receiving the light, say somewhere around 200 watts per meter square, the voltage in the panel builds up. But it is not necessary that it should give the rated amperage always. No, it gives along with the intensity of the light and along with the and considering the module temperature as well. So here we will find the MPP right beneath. It's highlighted in the green line. So that's the maximum power point of a solar photovoltaic panel. So when we multiplied the UMPP, or say the VMPP, by the current, short circuit current, then we get the rating of the panel. So that's why the panel is rated as watts peak. Solar strings. Well, in the industry, we may have to combine the solar panels in parallel or series. So when you put the panels in series, just similar to a battery in a circuit, when you put a panel in series, it's just connecting between positive to negative like that, right? So when you do that, the voltage adds. When you put them in parallel, then the current adds. So one loop of panel under which a single or a several panel in series is classified as a string, right? So you can combine these strings later also. You can basically put them in parallel also. This is very flexible, and it is as per the design requirement. And each of this string contains two cables. One is the positive cable, and the next one is negative cable. And the cable, when we are talking about this power cable, this comes with a higher specification and testing facilities, because these strings are often exposed out in the sun, so UV can damage the sheet. So it has undergone intense industrial testing in order to make them fit. Ideally, you know, when we make a solar utility scale solar photovoltaic system, the strings are rated to 1000 volts or even 1500 volts. So yes, we need to really take care of these cables. And ideally, we also use MC4 compliant plugs, because we need to interloop these cables. We need to connect them. So we use this multi-contact 4 type plugs, and these plugs are IP65. It's airtight and liquid tight and dust tight also. We really need to make sure that the ingress protection is really good, else it can cause a lot of trouble in the solar photovoltaic plant. The termination at the inverter is actually manufacturer specific. They may use MC4 or they can use their own connection technology. Now let's get into a little bit of details on what are all the types of solar PV systems that you will find in the market. The first and foremost is grid tie system. That's the simplest and largely used solar systems in the world. It's simple, and it is cost effective, and it is relatively less expensive as well. The next one is standalone solar system. I would say if you have a calculator with a solar panel in it, then it is an example for a standalone solar system. What it does is it is designed to cater to a dedicated load with the support of a storage, like a battery, over a certain period of time. Yep. The next is hybrid solar system. I should say that hybrid systems are better versions of a standalone solar system. So what if the battery dries out or there is a mechanical failure in the system? In that case, the hybrid system will have an auxiliary power supply, ideally from grid or a diesel generator, so that it can still cater to the load. Well, grid tie solar system. The grid tie or on-grid systems are really grid dependent. Why grid dependent? Because it cannot make its own grid. It comes with a transformer less kind of inverter, and it cannot cater to a dedicated load. What it simply does is it converts the DC energy out of a solar photovoltaic field into an alternating current, and it simply inject into the available grid. Please remember, it is injecting the AC into the available grid, right? So there are micro inverters, string inverters, multi-string inverters, and central inverters available for this kind of an application. The central inverters are used for systems from several kilowatts to megawatt scales, up to 100 megawatt scale. These are very expensive, and it can be equipped with a transformer also in order to supply the phases. The module or micro inverter is typically from few watts, say it's 50 watts to 500 watts. You will find string inverters from 500 watts to few kilowatts, and you will also see multi-string inverters from few kilowatts to few hundreds of kilowatts. Say I've seen up to 250 kilowatt rated multi-string inverter. Let's try to understand how this on-grid solar power plant works. This is an energy export model, an independent power plant. Here you can see there are several panels. They are in series. So what happens is during the daytime, as these panels receive light energy, it converts or it produces a DC energy, right? So this direct current, it reaches the inverter through the strings. And inside this inverter, it is getting converted into alternating current, and what comes out of the inverter later is an power cable, an AC power cable. Here it's an RYB, because assume that this is a three-phase inverter, and it goes through a circuit breaker and to the energy meter. Please have a close look at the arrow of the energy meter here, how or the direction of the AC flow. Yeah, it is towards the grid, right? So it is important that this grid must be active during daytime, so that this kind of system can export its energy into the grid. There are these inverters are very smart and sophisticated. The moment any of the phase is gone, it will stop production, because maybe the grid operator may deliberately cut the power lines for maintenance purposes, so they bring down the voltages, and in that point of time, the inverter must not give voltages into the grid, right? This is another model which we call the net metering model. The difference is that it consists of a domestic load. The earlier version is simply grid exporting, but here, in case if you have a house and you have enough space on top of the house, then you can consider this kind of system. Again, this is purely depending on what kind of the policy your grid operator provides, because not all countries supports these kind of solar photovoltaic plants. So kindly check with your grid operator whether you are legally allowed to install such kind of a plant. What this does is similar to the export model. It produces energy, right? But you can see there is a domestic load associated, and you can also see where the energy meter is kept. So this is the distribution board of your house. So whatever energy is produced by the inverter comes to this to the DB, from where you are actually taking in the energy, right? Here onwards, we are always talking in the terms of energy, not in terms of power. So your domestic load needs energy, and this energy is being drawn from the DB, where the DB is also catered with an in-house power generation. So in case if there is an excess energy, for example, your energy demand, say the photovoltaic production exceeds your energy demand, then there is excess energy, right? So that will go back to the grid. In the other time, for example, evening hours or night hours, there is no energy from the solar photovoltaic system. So in such situation, you have to take the energy back from the grid itself. So that's why kindly note, kindly remember, we use bidirectional meters, or we call it net meters for such kind of an application. Working of a string inverter. These are the bare minimum equipments that you will find inside an or a string inverter. To start with, we have a surge protection. And how do we do the protection? Because it monitors the amperes and it also monitors the voltage of the string. In case of an excess current or voltage, there are braking mechanisms inside the inverters. We use surge arresters and varistors, and different kind of protection is there. Then you will find MPPT trackers. Yes, it's very, very important, because MPPT is a device that always keeps a look at the voltage and current, and it tries to draw the best possible energy out of the system. Then the inversion circuit. In the inversion circuit, you will find it's the same inversion circuit that you studied back in the college. It just converts the DC into AC, and it tries to make the AC into perfect sinusoidal waves. There are harmonial corrections done. Then it comes to the sync circuit. The synchronization circuit, why do we need a synchronization circuit? Is because you are actually exporting your energy through the system into a grid. So the grid has different characteristics, right? The voltage, if it's a three-phase system, then the phase-to-phase voltage, the phase-to-neutral voltages, and end of the day, we have to consider the voltage between the neutral and earth as well. But the earth is generally in the building itself, right? So it need to try to tap into the grid by performing the energy into the same specification as it is available in the grid. Then only the syncing process is done. We need to make sure that the frequency is also synchronized, apart from voltages. These kind of inverters, you will not find a transformer inside, because it is incapable of producing its own grid. Then there is a grid monitoring. This sync circuit and grid monitoring works hand in hand, because that's how the sync circuit gets the information. Like if it is 240 over 415 voltages or 230 over 400 voltages, it's all depending on what country and what is the offered voltages in the, or say the declared voltage in the particular country. And of course, it requires a metering, because you need to quantify how much energy you have exported into the system. These are some of the photos. The bigger ones are Sunny Central. It is an SMA product. It is 2000, if I remember it correctly, it is 2.2 megawatt central inverters. Below, you will find these blue ones. These are 20 kilowatt inverters. The white ones, these are 50 kilowatt inverters. So basically, you get a wide range of inverters. So it all depends on how much space you have in your roof, and accordingly you can consider how much panels you can put. Then you can understand what size of an inverter you need to choose. When you find a data sheet of an inverter, there are a few things to identify with. So it always starts with the DC rating, or what are the accepted DC levels, right? So here you can see the maximum wattage offered here is 20,440 watts. This is for a 20 kilowatt inverter. You will also see this TL. The TL stands for transformerless. So the moment you see a TL, you can understand that these inverters are grid dependent or on-grid inverters. Then the next important thing is 1000 volts. That's the maximum input voltage. Ladies and gentlemen, please note that in case if you're going to design a solar photovoltaic system, please do not simply divide this 1000 volts with the open circuit voltage of the panel. Why? Because the open circuit voltage of a panel is only under standard testing conditions. So imagine a situation, there is enough sunshine and the temperature is 15 degrees Celsius. In that case, the open circuit voltage of the panel will go above what is shown in the data sheet. So that's a bad practice. So ideally, we have other simulation tools to really make sure that the voltage of the panel, the open circuit voltage of the panel, will not exceed the 1000 volts. But just for thumb rule calculations, for predictions, you can do that, but not for actually designing a solar photovoltaic system. Yeah. Then you can see the MPP voltage range. I hope you might remember what we shown on the data sheet of the panel. In maximum power point, the voltage of the panel will get dropped. So this is the range of this kind of an inverter, yeah, from 320 volts to 800 volts. But at the rated, or say the ideal voltage is 600 volts here. Then you can see the minimum startup voltage, because in inverters they have a little bit of self-consumption to start up. So just to start up, they need a bare minimum of 150 volts. This is again for this kind of a model. The smaller inverters may need even less voltage. So this is few things just to understand what are the characteristics of an inverter. Another thing is, you will find always a funny thing out of here. The power factor at rated power is unity. You know, back in the college days, we may have heard that it is not possible to have an electrical circuit with power factor to be 1 with unity, right? But this is not a joke. This is a reality. The string inverters, since it does not have a transformer and it cannot cater to an independent load, what all energy becomes the true power, right? The active power is just true power. So it doesn't have any apparent power associated with it. So when you make the triangle out of the when you try to analyze the cos phi, you actually miss the hypotenuse, right? So that's why the power factor is always 1 for this kind of an inverter. Some of the photos taken from site. These red and blue things are the strings that we are talking about. There are several panels combined in series, and these are the strings, and this enters a braking circuit and a metering circuit. There is CT to measure the current, and there are voltmeters inside this box. Then it goes to a surge protection device. These are the surge arresters. Then it goes into the inversion circuit. At the AC side, you will only see this AC connection ports. This is a 3-phase inverter. This is a 50 kilowatt 3-phase inverter. So what you can see is the RYBs here, and black, and the yellow-green. Here we use yellow-green for earthing. Yeah, so very simple connection. It is very easy to install. It's a plug-and-play kind of device. Standalone solar PV system. As I said earlier, if you have seen a calculator with a small solar panel in it, then yes, that's the best example for a solar standalone system. The advantage of a standalone system is that it is very flexible, and it is considered in places very far away from grid, or like an island or a secluded place, and you have an electrical energy demand, and you can put a standalone system there. There are a few things associated in solar standalone system apart from solar panel. First is charge controller. You need a battery bank, and you need an inverter as well. So these are the bare minimum things that you need. It comes from we often we size along with the battery scale as well. It comes from very few milliampere level battery to megawatts hour scale of storages. Huge battery banks are there. A typical standalone solar street is another example that you can consider. The small systems here, they use PWM, the pulse width modulated charge controllers. If your design system is less than 200 watts, but anything above 200 watts, you may consider a charge controller, an MPPT charge controller, because it's much more efficient in that case. This is a single line diagram of a standalone solar system. So let me try to help you how this works. Say during daytime, the PV bank here, the photovoltaic panels, it gets energized, yeah, and that's coming to the fuse. So why we have a fuse box in this case is because we are combining these strings. You see there are 3 strings. It is combined into 1 string. So the fuse box has a string combiner in it, and since we are using a string combination method, we can give them independent fuses to make sure that the reverse polarity doesn't occur, and also it gives an protection on the current side, right? So this goes to a charge controller here. In this system, actually we have done the system, and in the system you can see 2 charge controllers in action. So they must sync each other. So there is a communication between these charge controllers. It can be through hardware or it can be through Bluetooth, or it's all manufacturer depending, because these two charge controllers must sync in order to make sure that the terminal voltage and the charging algorithm is in action in a proper way. So from the charge controller, it goes to the battery bank. We combine several cells to make sure that the battery bank is of the right voltage setting. It can be 12, 24, 48, 36, 54. So different kind of charge controller, different kind of battery. We all consider these things when we do the design. So during daytime, these panels produces energy. The charge controller is a DC to DC. We will come to the DC to DC part. The charge controller is a DC to DC converter, and it injects that current into the battery bank. And when there is a load demand, these battery inverter converts the DC energy from the battery into alternating current, and it gives to the load. Let's see what is MPPT, a charge controller, and how it works. It's the similar to string inverters. These also use a maximum power point tracking mechanism. Let's start with the over current and over voltage protection. This is the first circuit you will find where the PV strings are connected. It goes to the MPPT tracker, which optimizes the energy. Then it goes to DC converter. You know, when we connect a solar string into the charge controller, the voltage will be around 600, or it can be 1000 volts, and the current is 9 amperes or 10 amperes. But you cannot put that directly onto a battery, right? Because the battery is, say, the battery bank is designed for 48 volts, right? So you need to convert the voltage and current in the input side into a different voltage and current setting in the output side. So that's why we use DC to DC converter. And when you do that, you will get, say, 600 volts of 9 amperes will be gone into 48 volts of, say, 70 amperes or 80 amperes, like that. So when you, after the conversion, you have to protect it at the overcurrent and over voltage again. Then the battery feed and monitoring device is also there. There's always keep an eye on the terminal voltages and how much current is being injected. And some good charge controller will also have a temperature sensor connected to the battery to make sure that the batteries are not overheating. Then it comes the battery bank. If you see a data sheet of a charge controller, you will find few information out of it which you really need to focus on. These charge controllers comes in different voltage settings. It is already manufactured, pre-programmed. You will see this 12 volt, 24 volts, 48 volts. It is not necessary that every manufacturer must follow this. Some is, if, for example, a good quality charge controller comes with different voltage settings. This is for the battery voltage side, and you can see the nominal power of PV. So in case if you are having a 48 volt system, then this particular charge controller can go up to 3440 watts, right? But if you are having a 12 volt system, then it is 860 watts. So these are the ranges that comes here. And also, there are 3 cycles associated to a battery charging stage, right? It is first is it starts with bulk, then the absorption, then float. So here you can see the absorption voltage is 14.4 for a 12 volt system. This is absorption happens when you are still injecting the current into the battery, right? So you can see how the terminal voltage is increased here. This is done by the charger. It just increases the output voltage so that it can inject the current into the battery. And also, when the battery is, say, fully charged, then it is given to 13.8. Here you can see it's for a 12 volt cell, and if you are combining that cell, it becomes a battery bank. And for that battery bank, you will find ideally for a 12 volt battery bank, the float is at 13.8. In some manufacturers, you can actually program this settings depending on what kind of battery technology you are using, because every battery technology have different float voltage levels. So you can actually program these things. Battery inverter. Here, I've used a term called battery string because that's the industrial practice. Anything with the DC cable, the positive and negative, we relate it as a string. Then the battery strings are connected into the over circuit, sorry, the over current and over voltage protection, and also a deep discharge cutout. Why do we need a deep discharge cutout? Is because you shouldn't drain a battery fully. Ideally, we keep at say 30% or 20% state of charge, at least. Beyond that factor, if you go, then the batteries can actually get dry, and it lacks its ability and efficiency to store charge. Yeah. So if the battery is having enough energy out of it, then it goes to the input monitoring. This basically works hand in hand, these circuits. Then it goes to the inversion circuit. There are some harmonic filters. Then it tries to make a perfect sinusoidal wave out of it. That's where the AC is produced, and it goes to the transformer, because we need a neutral, right? Because we are catering our energy into a dedicated load. So that's why we are using a transformer. We get a neutral out of it. We get a phase out of it. Then we feed into the AC load, which is a dedicated load. So what if there is a short circuit, or somebody added too much load beyond the capacity of the inverter? So it need to be break. So there is always a load monitoring, metering, and protection in the output side of the battery inverter. Hybrid system. As I said earlier, the hybrid system is nothing but a better version of a standalone solar system. What if you are having a cloudy day and you don't have enough energy out of the sun? So the batteries will eventually dry up, and the deep discharge or the battery inverter will monitor that the battery is not having enough energy. In that case, it will just shut down. So instead of going to darkness, these kind of inverters will have an auxiliary power source. It has a provision to connect an auxiliary power. It can be from a diesel generator. It can be from a grid power. In some cases, it can be from even wind turbines. So it's very flexible. In a hybrid battery inverter, it's similar to the previous inverter, just that here you can see right next to the transformer, there is an auxiliary feed. This is just a portion of connecting another source of power, and it goes to the AC load. That's the only difference between these two kind of inverters. Well, there are so much batteries here. As you can see, each of them are 2,600 ampere hours, and this is a 2-volt cell. So these are connected in series, and we made this a 48-volt system because that was the design requirement. You can see there are some terminal bus bars, which is protected very well, because accidentally no one shall touch that terminal bus bars. It can really kill a person. So we practice and we work with good caution at site. All the safety measures are taken. These yellow boxes are basically charge controller cum inverter. So this is a composite device. In previous slides, I have explained what an MPPT charge controller works and how a battery inverter works. When you put them together, you can get such device. Yes, for larger applications, these kind of charge controller and battery inverters are used. So here you can see the clusters to be in 3 pieces. So this is master, this is slave, slave, again master, slave, slave, master, slave, slave. Why this? Because this is a 3-phase system. So each of this inverter makes 1 phase. Yeah. So in order to make them a 3-phase system, we have this 3 inverter system. And these inverters also communicate in between to make sure that which phase. If one guy is producing R, then the other guy is making Y, and another guy is making B. So they sync in between. They have a thorough understanding in between of how they need to operate, and they make sorry, someone's voice is coming in between. I'd really request to cut off the mic, please. Perfect. Thank you so much. So this is the syncing mechanism. How this brain, the entire brain or the management work is through cluster managers. As I explained earlier, there are different clusters. In this case, it was a 3-cluster system. So all these 3 clusters needs to sync in, and it should work efficiently. So you can see a cluster manager. These are the stuff that you will find inside an ideal cluster manager. There are some contactors. There are this part, but it's not clear in the photograph. That's the brain. That's where the circuit board goes. All the IC chips and the programmable computer. It's a computer itself. It is designed with an algorithm on charging, discharging, and battery management, equalization, so float, absorption, whatever it is designed with these kind of capabilities. And this multi-cluster managers will instruct the battery inverters to perform its operation. There are some contactors, there are some provisions to connect. And here you can see this is actually a hybrid system where we are using the grid power. In case if the battery is down, then this grid power is used to cater to the load. Yep. Off-grid inverters. When you see this photo, you may have seen this photo earlier also. Actually, a good inverter manufacturer, when they make this solar inverters, it can be used as off-grid and it can be used as on-grid also. But still, it is transformer-less because the transformer is at the battery inverter side. So these are programmable. We can program it with an off-grid action because there is something called anti-islanding. The solar inverter, it must break its operation in case if the grid is deliberately cut. Okay. But in this kind of systems, we take away that part or anti-islanding part of this inverter. So we have to configure this inverter in what kind of application it is used. In case of an on-grid system, then we take out, then we make sure that the anti-islanding is on. And in this kind of system, the anti-islanding is off, so that it can produce its own independent AC voltages. But still, please remember, this inverters again is without transformer, it is incapable of producing its own grid. Various types of cells used. There are so much kinds of cell technologies available in the market, and there are several factors that we need to consider: the temperature, the amount of energy that you are going to store, what kind of battery bank voltage setting your inverter has, so multiple things. So every technology has its own advantages and disadvantages, and one of the commonly used is valve regulated lead acids and AGM batteries and gel bank. And you will find nickel cadmium also for deep discharge or deep cycle batteries with nickel cadmium. Lithium based, similar to your mobile phones, lithium based or laptops lithium based battery that are also used. Lithium cobalt oxide, lithium manganese oxide, lithium nickel manganese cobalt oxide, so different kind of lithium based. And there are also flow batteries, redox flow batteries and hybrid flow batteries. Unfortunately, I haven't worked with these flow batteries as of now, so I don't know much about it. I only know that these are being used in solar systems. Designing a photovoltaic system. Ladies and gentlemen, this is just an overview of how we design the solar photovoltaic system. This is not a presentation on how to design a solar photovoltaic system, because it requires several hours and training and a lot of field experience to get familiarized with the designing system. First of all, we need to understand what is the customer load profile. How much energy are we talking about? We do not talk in terms of watts, because watts comes later. First, we start with the energy. What is the demand energy? And how that energy demand is distributed. We'll come to that later. Available space, because if it's a ground, we need to see how much space is available. If it's a roof, then also we need to see how much space is available. Customers need, what kind of a system do they need? If they don't have much money and they have a stable grid, then on-grid systems are recommended. If they have a bit more money and they don't have a grid, then standalone system is considered. And if they want to dedicate a certain amount of your, say, a certain amount of the building's load into the system, and still you have grid connection as an auxiliary power, but you don't want to use it all the time, then a hybrid system is used. So basically, it offers a little bit of flexibility of how you need to make a plan and what kind of a plan. The product and technology availability, yes, because some inverters are not equipped for certain countries. So there are some restrictions. There are Japanese standard inverters, there are US standard inverters, some are Australian standard. So depending on the grid and the grid characteristics and the climate and so many factors. So we need to always consider the product and technology availability. The next is design viability. How better we can design for a certain kind of load. Then the budget factors, of course, end of the day, money matters, and maintenance factors. Here we have to consider the maintenance factors because every month we need to clean a panel. But where I am from, actually, in Kerala, we don't have to clean the panels because it can clean itself. There is rains once in a while, and there are no much dusty environment. So these are the stuff basically associated in designing. Now, the most important thing is the simulation tools. There are so many simulation tools because hand calculation takes weeks to do a proper hand calculation when you do simulation. The simulation is done through a computer-based software. Basically, it has the weather data. You can configure the system in that simulation tool, and you can virtually run it and make a performance report and understand how the system is working and if all design criteria are met, etc., etc. PVSYST, PVSol, Sunny, SMA Sunny Design. This is a manufacturer specific. You can download it from the internet, but it is exclusively for SMA products. Helioscope. They are some of the simulation software. So many softwares are available on the market. All inverter manufacturers, all good big scale inverter manufacturers are investing in their own simulation softwares. Load profile. This is a very simple that you can do from your home. All you need is an Excel or a spreadsheet based software. Here what I've done is I've plotted the time. If you have a better technique you may use, it's not necessary that you have to follow the same format itself. It's very flexible in this case. So you will find this time here, and simply you have to count what are all the electrical loads working during the time. So this bulb 1, I've put 10 beneath it. The 10 here stands for the wattage, yeah, because I'm quantifying the wattage in this case. So you can do this. Basically, anyone who wants to have a solar system in their home, they need to understand what is the energy being consumed in their home. A thumb rule you can do is you can take a reading from the starting of the month, and by the end of the month you will take another reading, and if you subtract, then you will find what is that particular month's energy consumed by your house. You can also do it on a daily basis as well, but we need a little bit of more information. How the hourly profile is. Hourly profile stands for how the energy distribution is done throughout a day. So these are some snapshots from software. Here you can see in the LED lamp, it is working in the evening hours, but the TV, PC, mobile, such kind of loads are throughout the daytime, and the domestic appliances, some of them are during morning hours. And when you do that, you can see the hourly profile, how it is distributed. So you have a little bit of loads towards the from 11 a.m. to during the early morning hours, and you have again too much loads in the evening hours. Why this is important is because the MPPT charge controller and the inverter and the battery, everything is parallel in a standalone system, right? So during daytime, the MPPT will increase the terminal voltage of the battery, and that same voltage is used by the battery inverter during daytime. So say if you are getting 60 amps out of the MPPT charge controller, okay, and it is coming to the same bus terminal where everything is parallel, and say 30 amps is taken by the battery inverter, and the rest 30 amps is injected into the battery. So that's how the daytime working is done. This is exclusively, it's not just for standalone system. In the grid tie system also, if you want to have, if you need to make sure that all your daytime loads are fully compensated by solar system, then you have to size it according to the daytime demand. In case if you don't want to pay any energy bill into the bill to the grid provider, and instead you only want to export, then you size the photovoltaic system in an on-grid system in a way that it can still produce energy more than your demand, right? So that's how the design criteria work here. Space availability in the roof. If you are in southern hemisphere, then the panel must be facing north. If you are in northern hemisphere, then the panel must be facing south. So that's the thumb rule. And as you see, the sun is not exactly above the head. It is above the head only in equator, but as you move further, you can see the sun's path, it follows a different angle. The good part is that there is some astronomy and physics also involved in this part of study. You may have heard that the two solstices, the winter and summer solstice, and there are two equinoxes. So there is a 50 degrees of phase shift happening, right? So when you have a horizon line drawing, this means the amount of solar irradiation over the time, and where is the sun rising and where it is setting, in what degree, and how much of energy is being drawn from the or what is the amount of solar energy available from the horizon. So we consider these things. Basically, this comes with the data, and this is already already fed to the simulation software. We don't need to do anything, just that it can simulate everything by itself. You also need to look out for shades, potential shades. It's very important because you are investing some money, you are designing a system, then ultimately if it is getting shaded, then you will not be able to produce enough energy. Even if it's a peak lunch hour or peak of the day, chances are likely it can still have shades. I'll come to that point in coming slide. This is suncalc.org. You can visit this website and see how the shading works. This is a wonderful website. Here I've done the calculation for Thrissur, where this engineering college is, who is hosting our webinar. This is the sun, the orange circle, and this is the sun's path, right? So you can input here the intended height of the building, or the calculated height of the building, or any obstacle. Could it be a tree, a building, a chimney, anything? Yeah. Then you can calculate how the shadow is working and what is the length of shadow. So please remember, here I've given, this is the 21st December as the winter solstice. You need to remember the dates of solstices to see what is the minimum shades and maximum shades in your respective country or place, or wherever you're planning to put a solar photovoltaic system. This is a basic tool to see how much of a solar photovoltaic system you need to make or consider. This is not an actual simulation software. This is just to visualize the results, a little bit of information. Anyone can use it, but please don't use it for actually constructing a solar photovoltaic plant, because this doesn't comes with the string configuration or the inverter specifications. No, it is just for an overview. Here I've done again the simulation for Thrissur. So we are going to simulate for 1 kilowatt peak of a solar PV system, and the system loss is kept at 14%. Just a rough thumb rule calculation. There are some inversion losses, there are some efficiency losses, there are some cable losses, etc., etc. It need not to be 14 always. Again, it is depending. Then we are going to optimize the slope and azimuth. This is very important. Please remember this, the slope and azimuth. Here we will find. Let's start with the slope. The tilt angle desired for Thrissur is 15 degrees. Wherever you are listening from, you can also check this. You can use this tool to understand what kind of a slope you need for the solar system. And azimuth angle is -1. Azimuth 0 means it's 180 degrees, exactly towards the south, not the magnetic south, but the true south. Here it is -1, which means 179 degrees. So that's the facing of your solar system. And if you build such a system, tentatively it will give 1,572 units of electricity. If your house is having, say, 175 or 250 units for 2 months, then ideally you are consuming, say, 1,500 units of electricity every year. And if you're going for a grid connected plant, then you need a 1 kilowatt system so that you don't have to pay any more bills to the grid. Or basically whatever you are consumed from the grid is basically what you produced. Please remember, in such systems, if the grid is failed, then basically you will not be able to export any energy. So that's a complete downtime and waste of energy in such situations. Let's come back to the point itself. So in this tool, you can also see how the distribution of energy is done, right? So this is done in Thrissur. So the June and July, when the monsoon season comes, the energy is very less because it's more or less a cloudy days. And you can see January and December and February, March, all these months, the irradiation is very good. There is too much shining sun, and hence it produces enough energy during good amount of energy during that time, right? The simulation of the system. The simulation tools are provided with information on basically all components associated to it. Maybe inverter, battery, charge controllers, solar panels, everything. Everything is input, right? These are all the factors that we feed into the simulation system. Then we also give them the panel orientation and the tilt and direction, right? Then the next is panel model, number and data, such things, and the planned inverter, string configuration, because we have combined, say, strings to 20 panels combined together to get around 800 volts up to 900 volts. So these are all tentative things. And the beauty is that the simulation softwares can check whether your design is correct or not. In case if you are exceeding the MPPT voltage, or in case you are exceeding the input voltage, maximum input voltage, it can give you a heads up. No, you are doing something wrong. You need to change, or you need to reconsider the design. So these are some minimum input. Also, the cable cross section and length. It's very important because sometimes we'll have to pull DC cables to several hundred meters. So a 4 mm will not work. In that case, we'll have to go for a 6 mm square cable or an 8 mm square cable. So, and also on the AC side as well, because the inverter is located far away from the distribution board. So if 25 mm square cable is, if it is having a voltage drop, then even though the inverter reading is right, but end of the day, due to the voltage loss, the actual valued energy is much less. So in such situations, we really need to make sure that the cable is correctly laid and we have correctly sized the cable to avoid the voltage loss. Ideally, it is less than 1% for the DC side and up to 3%, less than 3% on the AC side. When you do the simulation, you get a report out of it. And these are some snapshots from a simulation report. I've highlighted few things. There are so much losses associated. So this is basically the array nominal energy, whatever you get out of the system, right? And as you come down, these are all the losses happening in between in the due course. There are charge controller losses, efficiency losses, power threshold losses, converter losses, and the battery efficiency losses. There's so much factors affected. So not all the energy that you produced at the photovoltaic system is basically being used or effectively being used, right? Because there are efficiency and conversion losses involved in between. But when we do a simulation system, we always trust into these three key elements: the direct use, the stored energy, and missing energy. Direct use, as I said earlier, during the daytime, since the MPPT charger is providing a voltage, that same voltage is used by the inverter that is in parallel action, right? So that is the direct use. The next one is stored energy. So the balance excess energy after giving it to the battery after giving it to the battery inverter, the excess current goes into the battery. So that is the stored energy there. And missing energy. Coming back to this profile, for example, you have 1 kilowatt system, and that in the month of Jan and December, it is producing enough energy to cater to your load. But what if a monsoon season comes or a snow season comes? Then you're not producing enough energy. In such cases, basically, it ends up in the missing energy. That means that is the energy that you lack from the system. And ideally, if there are design or space requirement constraints, and if you cannot add more panels or increase the battery, then we will go for a hybrid system, because this missing energy will be catered by the auxiliary power. Some of the common mistakes: energy is the design basis, ladies and gentlemen. Whenever we talk photovoltaics, we talk energy, not just power, because say if your house demand load is 10 kilowatts, then if you put a 10 kilowatt solar photovoltaic system will not work because there are several variables associated. Probably you'll have to go for 30 kilowatt or even 35 kilowatt to cater to a 10 kilowatt system, depending on what kind of a system it is and your weather and the orientation, the location of the building, etc., etc. So always energy is the design basis, and I've explained how to calculate the energy consumed by your house. You can do this math. It's very simple. It's not a rocket science. Ideally, in case if you wish to go for a solar photovoltaic plant, always remember this energy. What is the units of electricity you being consumed every day? Undersizing the PV table and improper alignment. In case if you are in northern hemisphere and you face the panels north, it's of no use because the panel is shaded by itself. So it will not produce any energy. And if it is tilted towards east, yeah, during daytime, say early morning hours, you'll get energy, but in the afternoon, you'll not get any energy because again, it gets shaded. So these are some of the mistakes. You will also see improper shade analysis. Shade analysis is very important because at some point of time, at some point of solstice, it shouldn't make any sort of shade. If there is a tree near your home, you may not have a shade from the tree during June, but it can create a shade in December. So you really need to invest your time in proper and thorough shade analysis. Improper PV table orientation and tilt, improper cable selection and sizing. For DC, single stranded cables are used because the current flows through the entire cross section of a cable. But in AC, it more or less goes through the outer surface. It's called the skin effect. Yeah. So we use multi-stranded cables there. For AC cables, you will find this twisted pair cables. The negative, sorry, the phase and neutral, you can twist it and you get a cable like that. But in DC, no. For positive, it's a different cable. For negative, it's a different cable, and it is also laid in different. It can go in the same containment, but you shouldn't twist it and pair it. Yeah. So there are some do's and don'ts in cable selection and sizing. Wrong selection of inverter. You have 10 panels and you are not able to connect to that a solar inverter. That's a problem. So you need to make sure that the solar panel is chosen according to what type of solar panels and what are the wattage of the panel and how many numbers of panels you are intending to connect to it. Under or oversizing the battery bank. This is a key part because the battery bank works in a way that it stores energy and it stores and it also discharges. So that counts the cycle. So it comes in C10, C20. If you look at the battery data sheet, you will find different C of a battery. And if you put a huge battery bank, more than what you need, what happens is the charge controller may not be effectively charged the entire battery. There will be too much losses associated in that case. If you undersize the battery bank, what will happen is there will be still excess energy from the MPPT, but there is no place to, or there is no provision to charge the batteries any further. So the MPPT will just stop generating electricity. So that's the waste of an energy there. So another common mistakes done is the programming of inverter or charge controller, because if you put an off-grid inverter for an on-grid inverter, if it's a programmable thing, then you are causing a big problem. For example, if the grid is deliberately cut for maintenance purpose, and you have a wrongly configured string inverter connected to the grid, it can still cause a voltage in one side. So it is very dangerous. So these are some of the common mistakes that happens in our industry. Let's discuss a little bit of project management. This is just a single slide just to give you an overview how the project management works. So I've divided into 3 sections. Let's start with the pre-construction. Before we enter the construction phase, we qualify the materials. It is through something called a material submittal. It will involve the simulation report, the data sheet of panels, the data sheet of cables, basically the data sheets of all components that we intend to use in that particular system, and resumes of the engineers and technicians who are going to build it, the company profile, in terms of a contractor, like how good they are, the ISO certificates of different bodies associated, so etc., etc. So this is sent to the client or a consultant, and they will approve it, they will comment on it, and they will understand. And only when they approve, then only we will start basically procuring the materials from overseas. Because if I give them, say, a Tata solar panel, and then they say that no, I don't need this, I need something else. So that's a quality issue. That's a management quality issue, right? So we always make sure that the client is addressed very well. So once we get the material submittal approved, then we go for the shop drawing preparation. Because maybe in the last minute they say that the client doesn't need a particular brand, a different brand. So sometimes a different brand panel will have a different dimension. So we don't waste our time in the due course. Yeah. So shop drawings are often prepared after material submittal is approved. So the shop drawings will come ideally in 3 sets. One is an electrical drawing, the electrical layout, how it shows how the string configuration is done, what kind of cables are used, how the cables are routed towards the inverter, etc., etc. The next one is structural. Structural drawings plays a very important part, because in case of a roof, yeah, and if you're planning to put such a heavy equipment on top of a roof, then the architect or the civil engineer who designed that building need to verify that yes, you can have that kind of a load. And structural calculations are also used to see what are the wind effect on a solar photovoltaic system. Even if it is flat or even if it is tilted, you need to calculate what is the wind stress acting on the solar photovoltaic system. And these are the structural details. And the next one is single line diagram, so that any person who is going to review these 2 drawings can easily understand how the system is. So, and another single line diagram. During construction phase, we always start by preparing the site and the footing. Footing means it could be a floating plinth on top of your roof, or it could be just a substructure used to tether the mounting frame to the roof, or it could be a big concrete block for on-ground installation, etc., etc. The next is installation of support structure. Then once the structure is thoroughly done, then we put the solar panels on top of it. In parallel, and another team can actually install the inverters and data loggers and battery management equipment. It's a different room or in a different area. Once this basic installation is done, then we start the wiring and termination. Then we enter the testing and commissioning phase. We start with pre-testing checks. We will go in a little bit depth how this is done in the coming slide. To start discussing about testing and commissioning, we always need to have 2 values to relate to see how effective your plant is working, right? So in case of a diesel generator, you can measure the RPM or the energy produced by the diesel generator versus the turbines. But here it's sun. So what we do is we have an irradiation sensor. Sorry, someone's sound is coming. Sorry. Dr. G. Shelvaraj, sir, can I kindly request you to mute your mic, please? All right. So this irradiation sensor is calibrated, and it measures the sun, and it is always, it doesn't measure the sun, it measures the sunlight, and it is always kept in the same alignment of the panel itself. Then we also use something called a module temperature sensor, because as I explained in one of our first slide, the irradiation and module temperature plays a big part. So we always monitor the module temperature of a panel, right? Then we get something called a theoretical output and an actual output. We'll come to that in detail. Before we do the testing process, or even we energize the plant, the testing and commissioning team will go through the solar photovoltaic field to see any visible defect, to see if there is any cables hung loose, to see if there is any plugs that are not intact, because when you start up the plant, if there is a mechanical defect in any of the component, then it can actually cause a fire, and that's very severe. Because I hope you may have seen the welding, how a welding machine works, right? It's a DC arc, what you're producing there. So here we are talking about 1000-volt DC strings, and yes, it can create a crazy arc, and the arcs and shocks are really, really lethal. So there is a thorough checkup done before we even energize the system. So once it passes the energizing of the system, then only we will actually charge the cables, and we start up the system. So here is a photo of a battery inverter. This is the yellow inverter. Let me go back to the first slide just to understand. Here, when you open this inverter, that's the photo what we are going to refer now. This one. That's a 200 and 600 ampere hour battery bank and 48 volts. Now you can imagine if you accidentally short circuit this, it is going to create one hell of a problem. So safety first. We make sure that it's not just we, any good engineering company who does the installation of such system, make sure that the electrical resistant gloves are used, thorough checks of fuses. Fuses are done. For example, if you're going to repair this inverter, if you're going to do some connection or modification, we always make sure that the fuses are out from the fuse box. There are different kinds of fuse box available for this kind of, and there is a breaker also available, just a simple contact breaker. We put it in negative or positive, and both these are all possible in the industry. So just to understand the severity of what we are talking about. Cleaning the panels, another important thing, because if you are going for a testing and commissioning, and if the panels are dirty, then you will not be getting enough energy or the intended energy out of the system. So we clean the panels, and cleaning of panel must only be done with potable grade running water. Usage of detergents are really disregarded in the industry, as it accelerates the corrosion of aluminum, and it also make the glass damage. So we only use running water, and in case if we don't have running water, then we only use soft cloth mop to take away the dust from the panel. Here you can see how the unclean and clean panels looks like. A very good instrument that we use, it's a multimeter with a clamp. It's a composite device. It's a multimeter with a clamp meter. This is rated for 1000 volts DC service and up to 200 amperes the current reading. You can also see that accidentally, if you touch this bus bar is basically 415 volts. You don't need to accidentally touch this bus bar, so that it comes with a flex also. So we just need to loop it around the cable, and you can read. So before plugging, we always look for the open circuit voltage of the strings, and the thumb rule is similar strings, similar voltage. Why? Because if you have, say, 20 panels in series in one string, and if you have another string with again 20 panels, the open circuit voltage must be same. If the first string is giving you a reading which is 800 and the next one is giving 650, then definitely you can know that one of the panel is not producing the voltage, or there is something wrong in the string. Then also we check the continuity of the string. Maybe you will get the voltage from the positive side, but on the negative side you will not get. Sometimes you don't get, so there is an imbalance. So we can also look for the string faults. That's what we call the string faults. We can check just by checking the open circuit voltages. If everything is okay, ideally we start by plugging it into the inverter. We start up the inverter, we see its waking the sequence. The inverters will not immediately start producing AC current. It will take a little bit of time, because so much monitoring and MPPT tracking mechanisms are done in between that time. We see the startup sequence. In case of an off-grid or hybrid system, the battery characteristic, charge controller performance, and inverter performance are also measured and monitored. Weather data. Earlier we just showed you the irradiation sensor and the module temperature sensor. So this is what basically you get out of the system. That it is connected with the data logger, and from the data logger we get the readings, and you can plot it into an Excel. So this actually helps us to understand. You can see, please don't mind the module temperature curve. It is required, but not in this part. But please have a look at the irradiation. So that's the sun's path on that particular day, and you can see the time also plotted in bottom. And on this side of the screen, you will find a graph with multiple lines. So that indicates the wattage of that inverter. Here we have used 4 inverters, but you only see 2 lines. That's because 2 of the inverters are similar, and such 2 sets of inverters are used. So In case if either of the inverter has a fault or isn't producing to the desired level, then this graph will indicate it can drop or it can go above, or simply the line doesn't exist. So the beauty of the solar system is that everything is in a linear equation, and you can actually make use of such advanced technologies to actually assess the performance of a photovoltaic plant. Performance report. Performance report, as I said earlier, there are two values that we compare, the theoretical output and the practical output. So how do you get the theoretical output? That's the energy target. And the energy target is nothing but the computation of this equation. And this equation consists the peak power, the STC power, which is the standing testing condition power, the temperature coefficient, the degradation. Degradation plays, let me explain you a little bit about the degradation. If you plan to buy a solar photovoltaic panel, and that need not necessary that it will give its rated capacity throughout its life cycle, because it's an electronic device similar to your mobile phone. If you buy a mobile phone and after 5 years it is not giving you the actual performance, right? So there is a degradation always affected with the panel. So that's why there is a linear performance warranty term associated in such solar photovoltaic. A good panel manufacturer will give you ideally 25 years of service life, but they have a clause along with it that every year the degradation is 1% or more, like that. So the initial degradation we consider because the panels may be 1 year old. By the time it is shipped and it is exported to sun and to the testing and commissioning, it can take up to a year depending on the size of the photovoltaic plant. The next thing is performance ratio. This is something that we will find in the simulation report. When you do the simulation, it can show you the performance ratio of the photovoltaic plant that you are about to build. It is a composite of several factors into it. Then the time span, it is 0.25 hours, which is quarter of an hour. And in the table, in the green field, these are the input what we give into this. Actually, I've done this in Excel. The time is plotted here, and the irradiation from the irradiation meter also plotted here, and the module temperature. So this time, irradiation, and module temperature, along with these above mentioned power and characteristics, it runs through this equation to give you an energy target. So that is the theoretical output. Then we have an energy measured. This energy measurement is also done through a data logger. There is all the inverters comes, the modern day inverters comes with its own metering unit, and either through Modbus or through BACnet or another protocol, it actually relays all this information into another data logger, and the data logger records it, and we get it as an Excel sheet in a CSV format or different kind of formats. Then we use it here. So when comparing, you can see then the thing is we need to check for the entire length of the energy measurement. So this is done on a very shining bright day to avoid clouds coming in between, because every time a cloud creates a shade, the MPPT will get confused and we will not get enough energy out of the system. So because in energy target, it only runs the equation, right? But in energy measured, it is an actual practical value, because if there is a cloud in between, a shade has been caused, then the MPPT lags are there. But we don't have an MPPT lag provision in the theoretical measurement. So we run it for a couple of hours, ideally for 4 hours. Then we relay the value. Here you can see on this plant, this is a 232.65 kilowatt peak plant. It's a big plant. And on that particular day, theoretically, it should give 706.72 units of electricity. But in reality, it has given 722.52. Why more energy measured is because a good quality solar panel manufacturer will always have a positive threshold. If the rated capacity of the panel is 250 watts, then it will be a bit more, say 255, or say a little bit, or say 4 or 5% more positive threshold will be there. So that's the comparison part, and if it succeeds, the thumb rule is the energy measured shall not be less than the energy target. If it goes less than the energy target, then there is definitely something wrong in the solar photovoltaic system, which we need to address. Scope for engineers. Well, solar industry has shown a compound annual growth rate of 15 to 18 percentage in recent years, and we are expecting that to continue. But this year was very challenging. As you all know, the COVID-19 pandemic crisis is happening, and it has affected all industries. But this is a very promising field for engineers. Here you can see in the early 2012, the hydropower was, sorry, the wind power was growing. It's on a very fast pace growing, but then it settled, and the solar PV also was in competition. But as you see that the years passed by, and as it came to 2018, the solar PV took the market lead. It becomes a major market player. Opportunities. Well, solar panel, one of the prime thing that goes in a solar panel is silicon, and silicon is again a mined mineral. So roughly around 7,000 plus tons of silicon is produced. So civil engineers, mechanical engineers, material engineers are all required in that part of the field. But it's in general, because it's not exclusively for photovoltaics. It's for all inverter and mobile phones and computer and whatever electronics you need silicon. Then the panel and inverter manufacturers requires production engineers, EC and EEE engineers. Solar mounting structures manufacturers requires real good caliber civil engineers. So photovoltaic is not a business exclusively for electronics or electrical engineers, because the solar mounting structure manufacturers requires civil engineers. They calculate the dead load, the wind stress, they do the static analysis, etc. The EPC companies like me, because I'm from a mechanical engineering background, but I'm working for a solar photovoltaic. Photovoltaic is just a portion of my work. We also construct in solar thermal plants, and we also have micro wind turbines, etc. So basically, mechanical engineers are flexible. You can also consider joining EPC companies if you are smart enough to tackle the problems associated to photovoltaics. And definitely, electronics and EEE students will have enough knowledge and the fundamental knowledge of how an inverter works, how the power electronic circuits works, etc. So they are also welcome they are most welcome in EPC companies, and civil engineers also, because there is a lot of footing works done, a lot of mounting frame, static material works done. So civil engineers are also needed in the EPC industry. EPC stands for engineering, procurement, and construction. For those who are not familiar with this terminology, data management and SCADA. All the modern day inverter manufacturer invest a lot of money into the data management, and also the preparing the firmware for the inverter or charge controllers, because basically the charging process is done through an algorithm. So they need a lot of good electronic and computer science engineers to make the firmware accordingly. And also integration with SCADA. SCADA, I've only worked with with BMS integration is only done through Modbus and BACnet. I'm not aware if there are other provisions also available. So all the computer science, IT, and EC engineers are also required there. Simulation software industry, it is again a booming industry. Several simulation software manufacturers are coming. So this software requires a lot of computer science, electronics, and IT engineers. Apart from that, there are numerous research and development organizations, independent consultancies, original equipment manufacturers, EPC companies across the globe. Photovoltaic is a very big industry. So if you have a right skill set, if you want to be a part of the green mission, if you want to work in a green energy field, then photovoltaics is one field that you may consider for your career. Anyway, thank you so much. Thank you so much for patiently listening throughout the presentation. Let's proceed to the questions, please.
Yes, this was a really wonderful session with lots and lots of informations. So on my behalf, I would thank Mr. Rajat for giving this much information to the entire people. So This session is open for questions and answer. Those who have any questions, you can unmute yourself and you can ask questions, and then mute yourself so that Mr. Rajat can answer.
Hi, Rajat sir. Thank you so much for the presentation. I have a simple question. Can you hear me?
Yes, I can hear you. Please go ahead, sir.
Okay. I don't know it's a relevant question, but just for a curiosity, I'm asking. So when you refer to light, is it visible light only or not? Because I'm asking because in solar irradiation spectrum, like 5% of the light is from UV, and something like 43% is from the visible, and majority of the light, like 52%, are from near infrared. So are you able to use the entire spectrum in your solar cell, or like if not, what is the limitation that happen?
Okay, well, wonderful question. So actually, I'm not from a manufacturer side or quantum mechanics side of the industry. What I've read is mostly it converts the visible energy. And as you know, the atmosphere is filtering out much of the EM spectrum, the gamma rays and X-rays. Only minute amounts are coming. But when the EM reaches the Earth, the majority share is again with visible light and IR, of course, and UV. So mostly the visible light part is getting converted here because that wavelength is matching the excitation process done in the biasing of a solar photovoltaic panel.
Okay, perfect. Thank you.
Welcome.
Hello, Mr. Rajat.
Yes, I can hear you, sir.
Yeah, this is Dr. Vinay from Saudi Arabia. This is my one question that in the Gulf region, the solar radiations and solar energy is available whole of the year, most of the time. What is the basic reason they are not shifting to their power generation for this solar energy?
Well, that's a tricky question. The Middle East is blessed with enough oil and gas. So the main problem is in a solar photovoltaic industry, it is not capable to produce the same amount of energy throughout the day, right? And it is not practical to consider a huge battery bank, and it is not financially viable as well because every 3 or 4 years you need to change the battery, and batteries it's really expensive. So yes, there is a game-changing thing happening in the Middle East. They are also considering on-grid plants. But to make it completely self-sustained in renewables, it is not possible in a financial perspective still in the Middle East. But yes, there are so many plants in Middle East.
If there is problem of battery, why they're not on grid? Directly they can supply to grid.
Yes, they do have a plant. There is a 100 megawatt plant in Abu Dhabi. There are so many plants. But the thing is, it is not in terms of viability, because we have to consider the energy that is being consumed during nighttime as well, right? So making it completely off grid, it's not possible with solar with the limitations. But they are using another technology which is called as concentrated solar power, where the light beam is reflected and concentrated into a particular area in which the salt is molten, and that heat energy is used to run the turbine. So photovoltaics has certain limitations. You cannot run a country completely out of photovoltaics day and night. Just for saving purposes, you can use grid tie applications.
Okay, also maybe the maintenance problem because sandstorm, this decreases the efficiency of the solar. So this is daily maybe required to clean, or maybe after 1 week. That's why maybe.
That's also another factor. Yes, in the Middle East we have some crazy sandstorm and dusting issues. That's also a concern. But you know, there are everyday cleaning mechanisms also available these days. That's another wonderful part of it. There are cleaning robots and automatically cleaning machines that if you have a static installation or a tilting installation, there is a small machine with a broom in it, and it will run throughout the panels, and it will remove the dust.
Okay,
as it
like
goes.
car wiper.
Yeah, exactly. Yeah, similar to Car Viper. Yes. So these are all available in the market these days.
Okay, okay. And another things, this so sun tracking means movable solar plant is practically. You have any idea that it is working practically or not? Because big plant we cannot solar plate we cannot move with the sun tracking device. You know, this increases the efficiency from 20 to nearly 35% by moving the solar panel towards the sun rays.
Yes, let me tell you a little bit about the sun tracking. It is not tracking the sunlight, but it is tracking the sun itself. Because imagine if there is a cloudy, if it's a cloudy day and a cloud is obstructing the sun. So if it's actually, if it is tracking the light, then it will go away from the sun, right? The chances are likely that it will go away from. So this tracking mechanism considers the irradiation data, right? It the thanks to wonderful astronomers and physics experts, they have actually tracked the path of sun, and we know in which degree, which latitude, which angle the sun is moving. So these tracking mechanisms are provided with the sun path across all the seasons. So it will work accordingly. And yes, it's a working technology. You will find a lot of tracking solar PV plants in Europe, and it's working efficiently, very perfectly.
Okay, thank you, sir.
Most welcome, sir.
Rajat,
Yes.
there was a question in the chat box by Sylvester. What is the maximum efficiency observed till now?
Whoa, efficiency of what? Inverter or a panel? Well, the efficiency. I think it's panel. Yes, it's it is somewhere around 17 or 18, if my memory is right. Let me tell you a little bit about the panel efficiency. The panel efficiency is nothing but the wattage of the panel divided by the area of the panel. So when I came to this industry back in 2014 into photovoltaics, then what available in the market for 1.6 meters square is 220 watt peak panels. But now for the same size, we are able to sell 320 watt peak panels. So you see the efficiency ratio went very high. So if my memory is right, it is somewhere around 17 or 18%. That's the maximum figure I've seen.
Okay. And one more thing, any information about the panel used in satellites?
Well, actually, I was anticipating this question. The panels used in satellites is a bit different to the panel that are used here on Earth. The main reason is that, first of all, there is intense amount of gamma radiation, really ionizing radiation out there in the space, and followed by X-rays. So the panels there has a filter, or it is equipped with a cover glass that can actually prevent the harmful radiation to get inside the panel. They don't want heating of the panel there.
Okay. Then one more question. Okay, I think this is the same question. What is the difference between the normal solar panel and solar sail used in spacecraft?
Spacecraft has additional strength. Okay, the normal spacecraft, I think they mean the International Space Station or satellites. I think it's the same question, right?
I think it's the same question.
Yes. If, for example, there was an aircraft built with solar panels. They had a better version of the solar panel. It is made much more light, with as light as possible. And the technology was same. If my memory is right, it was monocrystalline cells used in that airplane, and it was made with as light material as possible.
Okay, I think from chat box, these are the questions.
Okay.
Does anybody have any doubts regarding this? One more question is, okay.
So by increasing the height of placing
cost of PV with BESS and PV without BESS.
Pardon, can you please repeat it once again?
Compare initial investment cost of PV with BESS and PV without BESS.
That's not a terminology that I'm very familiar with. I need to refer to what BESS means. Sorry.
Battery energy storage.
Battery energy. Okay, so okay. we only refer as BS, battery storage. Anyway, there is a 40% more cost involved in a battery, as a nutshell, as a thumb rule. If you want a thumb rule result, but battery storage is not just the factor, because, for example, let me tell you a little bit more about the battery. If you have a battery at home, what happens is every 4 years you need to replace them, 4 or 3 years. Ideally, you can give a 3,000 cycles of a battery, then you have to replace the battery after 3 or 4 years. So in that case, that cost also will come into when you calculate the return on investment. You also need to account that value. So in the investment perspective and in the ROI perspective, yes, battery systems comes with around 40 to 50% additional cost.
Next, is there any technical challenge of using lithium-ion battery in KW range? KW range.
It is used in lithium ion is even considered in megawatt scale as well. There is no technical challenge as long as it has proper charging and discharging cycles. They must be tested for such an application.
Okay. I think the questions have finished.
So in case if any of the audience want to get in touch with me, they can approach me via email. I've given my email ID there in the presentation.
Yeah, anyway, many people are asking about PPT, and I will share the PPT along with the speaker's mail ID with your registered mail.
Yeah, there is another interesting question that just came, the energy storage system in PV arena. Yes, there is a good growth in the storage mechanism. Several countries are going greener and greener, and several of them. Let me tell you a little bit of the UPS, how your house UPS work. Every day, the modern day house builders, yeah, they always consider to have a battery inverter inside your home itself to cater to that dedicated load. So what the solar industry is doing is they are challenging this, or they are taking leverage of this option that every house customers are doing. So instead of having an inverter, a battery inverter in your house that uses the grid power, it's going solar. So the energy storage is a good market and a lot of opportunities, and not just that, the market perspective, the technology perspective also. The efficiency of the battery is going above very high. The flow batteries are coming now. Fuel cells are also coming. So the storage is a very promising industry. For a 2 kilowatt off-grid MPPT system, can the complete 2 kilowatt load be run at the same time? No, that's not the right way of looking at it. A 2 kilowatt off-grid MPPT system means, I believe you might have referred to a standalone system, right? So 2 kilowatt of off-grid, that 2 kilowatt peak actually stands for the area of PV. It is not. It has got nothing to do directly with the load side. So the PV area is much bigger than the load. So if you have a 2 kilowatt load to be run all the time, then you may have to consider a 10 or 12 kilowatt peak of system when you design it. When would we can expect a solar cell with efficiency 25%? Actually, I was in a discussion with one of the manufacturers a few weeks back. I don't think so anytime soon, because this the change of technology, the efficiency in soldering, the purity of silicon, and it's just evolving. But let's expect, say, in another 3 or 4 years, we can expect such a change. Yes, you can use solar systems in vehicles. You can do that. Do the China-India conflict affect solar industry? I'm not qualified enough to answer that. Dustproof panel can be used instead of cleaning regularly. No, dustproof, we cannot make. Dustproof is, in our terms, is just ingress protection, that the dust shouldn't get inside the bus or the silicon or semiconductor of the panel. But the glass is generally dust repellent, but still there will be dust sedimentation. Here in Middle East, we struggle a lot with the dusting of the panel. The panel efficiency will not decrease by 2.5 percentage. The panel, okay, that's the question. Why panel efficiency decreased by 2.5 percentage the moment we install PV? No, it doesn't. It is. Yes, that's the initial degradation. It is not need not to be 2.5 percentage. There is 1% degradation is there. Good quality. It all depends on the quality of the manufacturer. The initial degradation is because once the panel gets sunlight, it starts production. A little bit of degradation happens inside the panel. That's how the electronics works. When you first charge an electronic circuit with an voltage, definitely it starts its degradation process. But ideally, from if I'm not mistaken, it's the annual degradation ratio is around 0.7% only. It's not a big factor. So that's why at the 25th year, still you will be able to get 80% of the rated capacity of the panel. Can organic materials be used for the construction of solar cells? There is no such a technology. We need to make NP junctions. We have to depend on minerals. Tinox and silicon has to use. Thin films are also used. Thin film technologies are also used. There are flexible panels, but I don't know much about the organic materials. How do we scrap the PV at the end of its life? Ideally, I would always recommend you to send this panel back to the manufacturer, because they can still extract the aluminum, glass, plastic, and even the silicon out of the panel. No need to scrap a PV panel. Anyway, there is less hazardous equipment inside a PV panel. Even if you discard it, it's not going to endanger the environment. But ideally, it is good because even though solar systems are considered as greener technology, the mining, if you browse for the mining photos of silicon, you will see how much environment are we destroying. So let's not add to that. Instead, if we can send this panel to a recycling area, they can extract everything out of the panel.
There is again one question, is repeating actually. Can we integrate it with the DAM as floating device?
Yes, we can integrate in it as a DAM, and I'm working on such a project as a private project. And not for actually building it, but I'm checking the viability for that. Hopefully, in a couple of months, I can present such a report.
So if it is placed in dams, then what happens when the water flow increases?
No, the water flow. Okay, actually, still I'm contemplating. Not me. We are a team. We are working on checking the viability. Yes, there are some technical constraints, not just the floating mechanism, but also the biotic, the flora fauna systems beneath the panel. Actually, I'm not qualified enough to answer that question at the moment. We are still working on it.
I think regarding the floating solar panel plants, some trial runs are being carried out in Kerala also.
Yeah, it is done on still reservoirs or open ocean in different part of the world. But here the question is on a dam. There are several factors associated in a dam. The thing is, the dam consists of fisheries and one source of money, and the water inflow outflow is also matters to be considered. And it is not a still; it is a flowing river. So we need to design a proper arresting mechanism in such situations.
There is one question about the economical considerations. Do you think installing solar panels in a middle class house is economical considering the cost of investment?
Yes. You can expect a return on investment by around 8 years, 7 to 8 years, in case if you are going to use an on-grid system. It is economical.
Another one, do air mass affect PV efficiency?
Yes, it affects the PV efficiency. So that's why they consider AM 1.5 as standardized value. Do you think installing solar panels in a middle? Yeah, I answered that. And how much charging time do we get on an average day here in Thrissur? Okay, you can expect around 6 hours in a good amount of energy. Not on a cloudy day, 6 to 8 hours you can expect. What are the major problems that we have to face while implementing solar in vehicles? In vehicles, the first thing is that you cannot have a tilted panel. You have to put it in perfect flat panels on top of it, because it's not necessary that you are always traveling towards the sun axis, right? That's one constraint. The second constraint is the dead weight, because you are adding more batteries and you are adding inverter and panel as a dead weight into the vehicle. So in that case, you're actually giving a little bit more load to the engine. Otherwise, I don't see any problem in having a solar cars or solar vehicles. We even have an aircraft that has flown across the globe just with solar power. Yes, floating panel is 19 crores when it compared with the 7 crore. I've read about this. It's very, very costly, and the technology is very complex. It should rise and it should go along with the water levels. Yes, it's very costly. Yes, a solar cell is fragile. It is fragile. I don't have photos in my PC right now, but yes, it is fragile. The moment the cover glass is shattered, you will still get a little bit of energy from the panel, but eventually it will degrade, because the moment the cells get in touch with air, it starts oxidizing. So eventually the purity is affected, then the solar panel is dead if you have a shattered cover glass. Can solar participate in grid frequency regulation? I didn't get the question. The solar power, actually, we have a synchronizing mechanism to regulate the frequency. How to install it in dam as a floating device? I'm getting a question from Mr. Rohit Mohan. Actually, I'm working on that project as a private work. I'm still not qualified enough to answer that question. We are working on it. Actually, I don't know much about the trend in India, so I'm not able to answer this question. India is an energy sufficient country. What we really need is spinning reserve. Do PV help in maintaining spinning reserves? Actually, I'm not qualified enough to answer that question. I really need to look at more trends to answer that one. Solar tiles are working on the same principle as solar panels. Yes, solar tiles. And there is something called building integrated photovoltaics as well, where you can sandwich the panel in between a polycarbonate sheet or a glass, which is flexible so at times. Yes, it's working in the same principle. The photovoltaics, same principle. The kilowatt hour per meter square of European countries are 1,600, but they invest more in PV. Why? They invest both in PV and thermal systems also, because the energy cost there is relatively high, and they have a high. When in comparison, they earn more, and also they want to invest in greener technology, not just for reducing the energy bills, but also they have a good commitment towards the environment. So, and the government is of course supporting them to come up with such projects, small micro projects that where they can use the usage of renewable energy at their home itself. Oh, C10 and C20. It's just the hour. The C10, that values is hour versus the ampere that comes out of a battery. So ideally, in the solar industry, we always consider 10-hour cycles. So that's the difference. So in the same data sheet, you will see C up to C10 to C120. So that's the ampere hour or the rated discharge current furnished in the battery data sheet. But in the solar industry, we use C10 because ideally we have a 10-hour cycle. Transparent solar cells, translucent solar cells are still available in the market, but it's very, very expensive. It is a common thing used in building integrated photovoltaics. And transparent, I don't know when it is available. 100% transparent, I don't think whether it is possible also. I have very limited knowledge in the manufacturing side.
Okay, I think the questions are over. Now I would like to invite Dr. Renu Abraham, postdoctoral research fellow of Pennsylvania State University, USA, for giving a feedback.
Hi, thank you, Jin sir. Hi, Rajat sir. Thank you so much for the webinar. It was really a nice presentation. First of all, solar photovoltaic is a hot topic, right, and an interesting topic as well. But usually in our colleges, we study the basics of solar cell only. But what is limited in our academic curriculum is that we don't know how to implement a solar cell in real life, or we don't know the industrial aspect or the industrial parameters. So I think from this presentation, everything was clear. So more than a theory-based presentation, we got something new that is not easily accessible for the student, for a general public. I think that is the highlight of the presentation. And of course, you presented everything really nice with real images. So it was more interesting as well. So thank you so much, sir.
Most welcome, most welcome. Thank you so much, Jitin, and the management of Jyoti Engineering College, SAB. Thanks for considering me as your presenter today. I think it's time to sign off right now. And once again, I thank you all the participants and all the audience who have especially participated with a lot of wonderful questions. Thank you so much. You may, if you want to get in touch with me in future associated to industrial practices, then you may do that. In case if you're a student, not for designing a house plant, because I don't have time for such things. But yes, I'd like to definitely support the students. So students, if you have any academic related questions, you please feel free to get in touch with my email ID. Thank you so much once again. Wish you all a good day. Take care. Bye-bye.
And
Thank you, sir.
Most welcome.
Christo? I welcome Christoph Lloyd, the student coordinator of this event, to propose a vote of thanks.
Thank you, sir. A warm good afternoon to everyone. I consider it to be a privilege to have been asked to propose a vote of thanks on this auspicious occasion. First of all, I would like to thank Mr. Rajat Shashindran, Senior Project Engineer, Powerhouse ME, Doha, our most valued invited guest. We also would like to acknowledge our gratitude to you for your efforts towards the webinar in spite of your busy schedule and delivering such an informative session. Thank you, sir. I, on behalf of the Mechanical Department, in association with the Association of the Mechanical Engineering Students and the SAE Collegiate Club of Jyoti Engineering College, extend a very hearty vote of thanks to all the participants, both external and internal, for making part in this venture and making it a success. Without your participation, this wouldn't have been possible. We expect your sincere participation in our future programs as well. We also would like to acknowledge our gratitude to our principal, Reverend Father Dr. Jason Paul Mulerikal, CMI, our campus head, Father Roy Joseph Vadaken, and head of the department, Dr. Biju PL, and the entire Jyoti family for their enormous support, guidance, and cooperation. I also wish to express my gratitude to the staff coordinators, Mr. Jidin K. Kuriakos and Ando Zakaria sir, who contributed to organizing this seminar until this last moment. Once again, thank you very much to all of you.
Thank you all participants, and thank you Mr. Rajat Shashidharan for your presentation. And I wish all a very good day, and we'll meet you soon. Thank you.